Good morning, guys. Welcome back. This is going to be 7.1. So let's go ahead and take a look at 7.1, which is going to be an important section that basically describes that the area underneath a density curve is equal to probability, which is also equal to proportion of population. So I'd write that down and kind of be familiar with that idea, and I'll explain kind of what I mean as we go through. The first thing we want to do is just look at some of the properties of the normal density curve, which is the bell-shaped curve that we've kind of been talking about throughout the semester. So let me just kind of talk about those properties there, and you'll see this purple box here in 7.1. But number one, it just says that the curve is symmetric about the mean, and so that just means that the area on the left hand side, this area over here, is the same as the area on the right hand side, and the total area is equal to 1.0, and area is equal to probability. So when we find the area, which is two-dimensional space, right? Area, the carpet, you need to carpet your floor. How much area is that? Two-dimensional. Area is equal to probability, which is equal to proportion of population. P-R-O-P. Okay, proportion of population. So total area is 1. We have inflection points. It's not that important. Number 4 is, like I said, the most important. Left-hand side equals right, and we've already talked about the empirical rule. And the only other property is that asymptote property. It just says that as x gets really large, so this curve here, it gets really close to the x-axis, but never actually touches. There's always that tiny little gap in between. So those are the properties of the normal density curve. So let's look at a very basic density curve, which is called the uniform distribution, because areas for uniform distribution are really easy to calculate. If you kind of think about, let's just say that you wanted to calculate the area from this point back, so all this area in here. Well, that's not really a rectangle or a square or a circle. I don't know what kind of shape that is, right? So how do you find the area of weird shapes? That's what we're kind of eventually going into here. But uniform distribution, the areas are really easy to find. So I want to give you a definition of a density function. It's an equation used to compute probabilities, or we can replace that with areas, of continuous random variables. Must satisfy two properties. Total area under the graph of the equation for all possible values of the variable must be equal to 1, and the height of the graph of the equation must be greater than or equal to 0 for all the possible values of the random variable. So continuous uniform distribution is what we're going to look at. And the density function, the only thing really we want to pay attention to here is that the density function is 1 over b minus a. And it's defined on this interval here from a to b. So let's look at some examples here. It's number 18. Uniform distribution, okay? The reaction times of a certain chemical process follows a uniform distribution with 5 to 10. So time, x in minutes time, is from 5a to 10b. Okay, and so x, we'll say x follows, and this just means follows, uniform from a to b, so a is 5, b is 10. And so now we can plug in and get our density function here, right? Our PDF, remember, is f of x equals 1 over b minus a. So 1 over 10 minus 5 gives us 1/5. All right, and you can think about replacing f of x with y equals 1/5 if you want to. Okay, draw the density curve. Well, that's kind of easy to draw, right? So we just draw a rectangle from 5 to 10. That's x. And f of x, the density. And the height, f of x, we just found was 1/5. So 1/5 here. And then we'll just draw. Okay, And that's all there is. We've drawn the density curve. And you can notice the length of the rectangle is 10 minus 5, and the height is 1/5. So 5 times a fifth is 1. So the total area, this total area here is 1.0. And those are the conditions that we have to meet prior. Okay, so part B. Find the probability or the area under the curve that the reaction time is between 6 and 8 minutes. So we'll just do that here. So 6 and 8 minutes. So 5 to 10. 1/5. And we'll go 6 to 8. So we're wanting to know this area here. So what's the probability that the reaction time is between 6 and 8? Well, that's just going to be the area of this rectangle here. Notice the length of the rectangle here is 2. 6 to 8 is 2. And the height is 1/5. So 2 times 1/5. 2/5. 40%. Okay. All right. C. Okay. 5 to 8 minutes. So you know what's going to be going on here, right? Same thing. 5 to 10. X density. 1/5. So C says what? 5 to 8. Okay, so 5 to 8. So this is the area that we want here. So probability from 5 to 8 is equal to 3 times 1/5. 3/5. Okay, and D, less than 6. So I tell you what, I'll let you guys try D. You try D. I'll give you a second. You can pause the video. Okay, so let's see if you got the right answer here. Less than 6, so that's going to be 1/5. So the probability that X is less than 6 is 1/5. Okay, so wanted to show you a quick example here of what we're going to be doing. So let's say that we have a normally distributed random variable. So what we say here is X follows a normal, like we did for the binomial, with two parameters: the mean, population mean, and population standard deviation. Okay, the mean is 10, the standard deviation is 3. So this is the normal curve, normal with mean 0, 1. This is what we call standard normal. Very important, standard normal distribution. And this one down here is non-standard normal distribution. And we say that X follows this normal with mean of 10, standard deviation of 3. And X follows this normal as 0, 1, always standard normal. 0, 1 tells us it's standard normal. Compute the z-score. So what we're going to do is we're going to take values of X and we're going to convert them into Z. And actually, this over here, we need to start calling it Z. So let's say Z. Z follows standard normal. So anytime I say standard normal, I'm really talking about, and you'll see this is Z, not X, but Z. So what we're going to do is we're going to convert X's into Z's. So let's find X1 is 8, 5, 6, 7, 8 right here, 10, 11, 12. So we're going to convert these X's into Z's. So we do that, and we get Z equals 8 minus 10 over 3 minus 2/3 minus 0.67. Okay, and z equals, what's that, 12 minus 10 over 3. So we get positive 2/3, which is 33 and 30. This is 0.67. So we've got these x's go to z's. These x's go to z's. So we've got minus 0.67 and positive 0.67 here. These are the minus 0.67. And what we want to do is notice this area here in between these two lines. It's going to turn out, and the question is here, the area between 8 and 12 is 0.495. So the question mark is, what's the area in between minus 0.67 and 0.67 positive? Well, it turns out that for any normal random variable, we can always convert that into z-scores and calculate area, which is what we're going to be doing for the rest of the semester. So it turns out that this area here is also 0.495. Okay? All right, so that's 7.1. I wanted to share with you the importance of area under the curve being probability. And this one here you can explain, you can try to work through this one here. Okay, so fantastic, 7.1, and I will see you guys back for 7.2.